Hi, Seb here. Thought I'd finally take the opportunity to make a bit of like an overview, getting started tutorial on what this Eurorack PMOD thing is that I've been working on for a while. So what this is I would say it's kind of an open hardware audio interface with a whole bunch of examples that makes it easy for you to get started in the world of FPGA development in the context of audio, and specifically for this module in the context of Eurorack, so hardware audio synthesizers. So I've got a little toy Eurorack system over here that we'll play with a bit later, but for now maybe it makes sense for us to just look at this thing. So how do you actually get one of these? It's open hardware. You can see on the back, certified open hardware. So you can build one or you can buy one. I ship these, and each one of these I also ship with a little ribbon cable that you can use to connect to your FPGA board that you decide to use, and another ribbon cable that you would use to connect the Eurorack PMOD hardware to the Eurorack power bus. So on the left here you can see the power bus itself, and on the right the standardized PMOD interface. This PMOD interface can mate to a whole bunch of different FPGA boards. I just have a couple of boards here that are supported out of the box by the examples, but there are more supported. So today we'll be playing a lot with this Icebreaker. This is from 1-Bit Squared. The Pico Ice here is another nice Ice40 FPGA board from tinyvision.ai. I also have here a Epic 5. This is an absolute monster, and you can do some more advanced things if you have a big FPGA like this. Like for example, I have a USB sound card example project that lets you use this board plus the Eurorack PMOD as a USB sound card. But first up, let's go through the features. So this thing has, if you look at the front, so it's got like a little panel. Maybe I can fix the focus a little bit. Yeah. So on the front panel, you can see there is 4 input jacks, 4 output jacks. Each one of these can support plus minus around 9 volts, absolute DC swing. And each of these little rectangles is an LED indicator, fully programmable green-red. By default, out of the box, these LED indicators just show you what the voltage levels are at the inputs and the outputs. And then each of these jacks is this is an interesting feature. I kind of added it because I was wondering if it would be possible, but each of these jacks is actually also proximity sensitive. So if you don't have a jack plugged into these jacks, you can use your finger as like an input mechanism, which might be interesting if you have a modular system where you maybe you don't have so many modules, or you don't want to patch all of the inputs and you want to use them for something else, or whatever you want to do. But just for some of the detail here, the codec here, this is an 8-channel codec, 4 inputs, 4 outputs. It can run at 192 kilohertz. The examples out of the box, they run at 48 kilohertz sample rate. Then on the right and the left here, you can see this op-amp scaling network that scales the codec inputs and outputs to Eurorack voltage levels. This chip is an I2C basically GPIO expander that lets the FPGA tell if any of these jacks actually have the jack inserted. So each of these jacks are switched, so you can detect where the jacks are plugged in. There's a little, right at the top here, there's a little calibration EEPROM that you could write to if you want to write calibration to the device. There's a voltage reference and a buffer here. This little tiny chip is like a little Cypress touch sensing chip that does the proximity sensing on the front. And this big guy here is the LED, the 16 channels of LED driver for each of these little, you can see maybe a little bit, these tiny pair of LEDs here that couple through the PCB, through this diffuser, over to the other side. So yeah, maybe I'll just plug it in and we can try out some of the examples. One thing I just want to reiterate is in this video, I'm just going to be going through the Verilog examples, these basic Verilog examples that are included in the main repository in here, because I think they're the easiest to understand and get started with, and they also compile really quickly, and it's easy to understand how everything works because everything is in one repository. But there are some more sophisticated examples that I've put together for bigger FPGAs. For example, if you go up to the organization level, I have a few interesting things here. So this is the base repository. I also added an example LiteX project. This project is written in mostly Rust and Mygen, which is a Python-based hardware description language. So this is kind of how you can do DSP on a bigger FPGA with a soft core, RISC-V soft core with firmware that's written in Rust. I have another example here that is written in Amaranth, which is another Python-based HDL that lets you use the Eurorack PMOD as a USB sound card, or if you have an FPGA board that has a USB 2 interface. And I have another example here that lets you simulate Verilog inside VCVRack, which is a Eurorack simulator. But what I want to focus on today is just the basic Verilog repository, because I think it's the best place to get started. So here's my toy system. I've got a few basic modules in here that we'll experiment with today. Over the left, I have a disting programmable, like basically it's a multifunction module. I'm going to use it as a voltage source today for when we're doing calibration, but you don't need one. This is just for the sake of having everything on one screen. This is oscillator plats for mutable instruments. This is a bunch of attenuators, so I can get -10 to 10 volts on a pot here that is nice for driving the inputs of the Eurorack PMOD. And here I have basically just an output module that I'm going to route into my audio interface so that hopefully you can hear what I'm doing today. So as far as the Eurorack PMOD goes, all I need to do is take it, obviously, and then I'm going to go ahead and plug in the power bus ribbon cable, which comes with it. I'm going to go and plug in the PMOD ribbon cable. So that looks like this. Now I have these two ribbon cables kind of hanging off it. And the way I like to do things is I will just kind of fly the ribbon cable out of the subassembly like this. So first I just plug in the power bus, and then I will screw in the PMOD itself. Alright, so now the Eurorack PMOD is just kind of sitting in there, ready to do something. And so I'm going to push it over here. And now that we have this ribbon cable coming out, I've connected it up so that the stripe on the PMOD connector is further away, so not close to the 3.3 volt line on the pinout on the bottom of the board. Just so you know, on the bottom of the board here you can see what the pinout actually is of the connector here. But I've connected it like this, and then if I go ahead and take my icebreaker, then I connect it in the same way so that the 3.3 volts is on the same line, the same side of the ribbon cable. Now, the order I like to do things is I'm going to first plug in the power to my Eurorack system. So you can see the lights came on over here. Nothing's going to happen yet because we haven't flashed anything to our FPGA. But if I just move this over here, what I'm going to do now is just connect the FPGA dev board. And now we can, try one of the examples. Actually, I decided to move it over here so that I can fit everything on hopefully one half of the screen. Perfect. Now, to actually make the PMOD do something, first thing you want to do is go to the Eurorack PMOD repository. Let me see if I can get that on one screen. There we go. Here we go. This is the Eurorack PMOD GitHub repository. Here you will find some example projects from the community, a guide to what the hardware looks like, a guide to all of the example cores that you can compile for the system, the supported FPGA boards, the pinout, how to install the toolchain on Windows, Linux, and Mac. That's all here. And once you've gone ahead and cloned the GitHub repository, the best way to get started is with one of the simpler examples. So if I go ahead and look at the repository and I go to the gateware directory, here's where all of the, here's basically the example gateware that you can start playing with. And in the cores directory, there's some example projects. But if I'm here and I have the all the toolchains installed as per the README and so on, and I just type make, then it will tell me, I need to type in which hardware revision I'm using, I need to type in which board I'm using, I need to type in which core I want, and so on. Okay. In our case here, we're basically doing something very similar to this. We want hardware revision 3.3, we were using an icebreaker. The call we want is, let's try one of the even simpler examples, the mirror core. And then I'm going to do it without this prog target. The prog target will program the FPGA board after it goes through with synthesis. Actually, maybe I'll do it, yeah. This isn't supported for all of the FPGA boards. Sometimes it just gives you a bit stream that you need to flash with whatever tool you need for whatever tool you get for the FPGA board you're using, but I'm going to use prog in this case. And so if I go ahead, it's going to synthesize the example design, which really does not take very long on the ICE40, fortunately. And then it will program the FPGA board. And so now, the FPGA board is programmed. But how do we know whether it's actually succeeded? So the mirror core, the one that we just downloaded, if I go ahead and what it will do is it will take whatever is coming in on input 1. Obviously that will go be serialized, sent to the FPGA, come back, and then come out on output 1. And the same with input 2 will go to output 2, and so on. So this is a very simple way of testing that things are working. So if I go ahead and I just take this minus 10 to 10 volt pot that I have here, and I just patch it to input 1, and I start playing, you can see, hopefully, that both input 1 and output 1 of the Eurorack PMOD are changing, the same as, basically they're just mirroring whatever I'm sending in. Now if we want something a bit more interesting, we can go ahead and pass through the oscillator over here. So if I go patch the output into input 1 and then take the input and plug it into the mixer so you can hear what's going through the Eurorack PMOD. Yeah, so this is a simple way that you can kind of check the audio quality and the pass-through is working correctly. I like to test all of the channels as well. Make sure that they're all going through correctly and so on. But once you've verified that this works, you can go ahead and try some of the other examples. So yeah, let's, first I just want to show you what this core looks like that we just ran. So this is the mirror core. Each core has a similar interface where you see the samples coming in, you have a global sample clock, you have a faster clock that's used to run most of the other modules in the system. That's 256 times the sample rate. But in this mirror core case, we just assign the output is always the input, and that's a combinatorial assignment. So yeah, that's what we were just running. So there's a lot of hidden detail here, as you can probably imagine. If you look in the drivers folder, here is a driver for the audio codec itself. a driver for the I2C interface. This deals with the jack input detection and the touch sensing detection and the codec initialization and stuff like this. There's also an online calibration module that compensates for the DC offsets in the codec itself, so that you get really some nice absolute DC accuracy. All of these things you can modify. The calibration process itself I will show you a bit later, but yeah, for now let's just try something else. So here is in cores. We have a few different examples. One interesting one for us to try might be, let's try the clock divider. So same invocation that I had before. I'm just going to change core to the name of this core, so clock divider. Over here I have a kind of like a clock source, I guess. That's what the disting is currently doing. So this core, if we take this clock source now, it's already been flashed to the FPGA. We route this into input 1. The clock divider example is a bit of a weird one because it, if you look at the implementation, see it says output only becomes active if the jack is inserted. So it actually makes use of this jack detection function. And you can see here this output is forwarded only if the jack is inserted in this clock division logic. That means that you can see the clock is coming in, but nothing is coming out unless I actually patch something in. So if I go ahead and patch output 1, I can see an output that's a bit slower than the input here. If I patch output 2, that's even slower. But if I go and take this clock divided output and patch it to the audio, you're going to get something pretty terrible. I'm going to turn the volume all the way down so it's not going to kill your eardrums, hopefully. If I actually patch in the VCO instead of a clock source, then you can get some kind of interesting results. So if I patch in the VCO, you can hear that's being divided, or divide by 2. It's almost kind of behaving like a bit crusher almost when you connect it like this. Anyway, let's try something else. I'll just show you a couple more examples before we move on. So one of the ones I like is the pitch shifter. So pitch shifter is based on a couple of delay lines that fade between each other. So they kind of take the input, slice it into short chunks, play them one after another and crossfade between them at different speeds so that you end up with kind of a pitch shifting effect. And I'll give you an example of how that sounds. If we go ahead here and we just build the pitch shifter example, doesn't take very long. Here I will take my oscillator again, patch it into input 1. Then output 1 in the pitch shifter example is just going to be the input. So, not very interesting. Output 2 is going to be the pitch shifted version. At the moment it's just the same. And output 3 is going to be the two of them summed together. So if I take the pitch shifted version, and then I take input 2, which is the pitch shift amount, which is controllable with CV, and I patch it into the output here, I can start to pitch shift the oscillator that I'm running into the interface. But if I take output 3, this is the sum, remember, we end up with a strange kind of harmonizing effect. We've got the original oscillator coming through and then the two of them summed together. So I've got kind of two pitches created from this one oscillator, which I can move around. And in the implementation, you can see input shift, how the outputs are routed here. We have the transposer, output 0 is just input 0, output 2 is input 0 plus input 1, shifted so that we don't saturate the output and clip. Last one I want to show you here is the touch example, because it's a bit different. There's more. I'm not going to show you all of the examples, but the touch example needs, as you can see here, we can select whether we want touch sensing enabled or disabled. If you want the touch example, you need to enable the touch sensing core. And the reason is because the touch sensing core, it turns on capacitive touch sensing of all of these jacks. And the reason I made it selectable is because the noise performance actually suffers just a little bit. You can barely hear it if the touch sensing is on, and for that reason I made it so that you can choose whether it's on or off. So if I go touch sense enabled with the touch CV core, and I just unplug all these things as well, now it's just flashed the board, and if I go ahead and touch these knobs, you can see the lights come up at the bottom. And that's because if you look at the touch sensing core, it takes output 0 is the touch sensing on the first row, scaled by some amount, and it's the same with all of the outputs here. So what this is doing is it's taking the continuous capacitive touch sensing values in the first four input jacks, and then outputting them on the last 4 jacks. So you can take the output jack 1, for example. I could hook that up to the level of my oscillator. I can take the output of my oscillator and then route it to the audio interface. So now I have my the level of my oscillator is being driven by the CV output of the Eurorack PMOD, which you can modulate with the sensor here. I could add another one. Let's take touch output 2. I'll put it on the timbre of the oscillator. Now I have 2 inputs. Yeah, so it's kind of interesting, some interesting stuff you could potentially do there with custom cores. I think that's as far as I'll go, as far as the example cores go. As you can see, there's a lot of them. And yeah, you can feel free to try those out. But what I would like to do now is to go into a little bit more detail about how the hardware works and how the calibration process works if you would like to calibrate your Eurorack PMOD. And one of the reasons you may want to calibrate it is if you are using it to tune other oscillators which need a bit more accurate tuning voltages. So when I send these out, they are not calibrated. Could do it myself, but it just saves a lot of time to not do that. Out of the box, you will get between 50 and 100 millivolts of absolute tuning accuracy out of these things without calibrating them. But if you want to calibrate them, I will show you how. So as far as calibration goes, you really only need to do this if you need really precise DC voltages, which you might need if you're using the Eurorack PMOD to tune oscillators or something like this. And the procedure is pretty well documented, I think. So the story is the codec that is used in the Eurorack PMOD hardware design. If you have a look at the input side, the input scaling is directly coupled. There is no capacitor here to the codec inputs, and the same story on the output. You can see the codec outputs, they make their way without a coupling capacitor into the op amp here, and that has the consequence that we can use this codec at DC, which is not really what it's designed to be used. The way it's designed to be used is not this way, but it does mean that if we want to have kind of accurate DC levels, that we need to calibrate it. So the story is on the FPGA itself. we have this calibration core that is automatically included when you build things. And what it does is it takes a calibration hex file, which is a bunch of constants, and it uses those to scale the scale and shift the readings in real time from the inputs and to the outputs, so that we can zero out any biases that are inside the codec. And that's kind of described up here, what it actually does. But you'll see that included in the repository is a calibration script, cal.py. And at the top of this, it describes what you need to do to be able to calibrate one of these modules. So it says you need to compile the gateware with a special output calibration flag enabled. You need to connect the inputs to a voltage source, run the calibration utility, and then basically follow all of these steps. So one of the interesting things here is the output impedance of the Eurorack PMOD is 1K. And that has consequences when you're trying to calibrate things, because usually in Eurorack, I think it's not completely standardized, but at least in this module and in a lot of other modules, the input impedance is generally 100 kilo ohms, and the output impedance is in the order of 1 kilo ohm. And that means that the output of this 1 kilo ohm, if you connect that to another module that has an input impedance of 100 kilo ohm, that becomes a voltage divider. So you can actually select in the calibration utility if the calibration process assumes that the outputs will be connected to a 100K load, which is normally the case, or not, which would be open load. So the default is currently open load, and the reason I have the default set to open load is because that means if you measure the output of the Eurorack PMOD with a multimeter, then it will be accurate because the multimeter has very high input impedance. But as soon as you connect it to another module, then the calibration would be out unless you set this to false. But long story short, follow this process. If you're testing with a multimeter, then you can use this open load flag. If you're not and you want to connect it to other modules, then you can switch that to false. The whole calibration sequence happens here, and what you'll get at the end is a new hex file that you can integrate into the build process, so that when you run the examples, it uses your your new calibration file. First step, compile gateware program FPGA with these defines output calibration. That's not so bad. So if I go top and I uncomment this output calibration define, and I go ahead and let's make the mirror core. That's the one that you want for this. And while this is going, I might just disconnect everything that we have connected here. We definitely don't want to listen to what's going on when this happens. And okay, so now we've flashed with output calibration enabled. You can see that all the LEDs at the bottom have just come on. That's because it is forcing the outputs to a specific voltage. And at least on the icebreaker, the output calibration mode connects the button here to the output voltage. So if I press it, see how it switches from red to green? So that's switching from -5 volts to 5 volts output. So you can measure what the actual... what this is doing is it's sending, in theory, exactly +5 volts and -5 volts to the output. But in reality, it may not be that. So that's why we have to calibrate it. That's why we have to flash the special gateware on here so that we can calibrate it. But I'll just take you through the process now. Now that we have the special calibration firmware flash, let's have a look at what the instructions were again. Connect a voltage source to all of the inputs. Okay, you could use a lab power supply if you want. I will not. I will use this thing. So if I change the algorithm to a 1 on the disting, I mean, you don't need a disting for this, but what this will do is it will give me a precision voltage source. So now I have minus 10 to 10 volts present on these jacks here. The way the calibration tool works is the example gateway has a little serial, a bit of serial gateway in it, so that all of the data that you want from the raw ADC values and so on is sent over serial. And you can see that in this debug UART implementation. So here it takes all of this information and sends it out the serial port. So you can look at it. You can look at it just using a normal serial terminal. For example, if it looks like it enumerated on TTY USB 1. Or not. 2? Yeah, okay. So here's a bunch of crap. But what does it actually mean? Well, this is all information coming from the icebreaker in like a binary stream. But if I run this cal utility, it was TTY USB 2. So there we go. Now we have the calibration tool running. I'm just going to send this away so you can see the whole thing. So it says input calibration. Here is some information from the Eurorack PMOD that's been sent over serial. If I go ahead and like look at, for example, there's a lot of other signals here. So if I touch the jacks, that's not going to do anything because I have touch sensing disabled. But if I plug something into one of the jacks, you can see jack changed from 0x1 to 0x9. That's the raw jack reading. You can see the serial of the EEPROM and so on here. And then the most useful thing is this raw ADC sample. So this is what's being read from the codec. And you can see if I change the input voltage here, that the raw ADC samples is changing. So here, what you can go ahead and do is connect all the inputs together, as it says here. Connect the source to all of the inputs, supply 5 volts, and wait for the values to settle. Okay, so I'm going to go ahead and do that. All of the inputs connected together, and at this point you can see that if I change the input voltage, all of them are changing. And interestingly, if I set it to 0 volts, you can see the raw ADC input is not 0. It's close to 0. You know, this is you have to divide all these values by 4 to get the interpreted, because I use 14.2 fixed point representation. So all of these divided by 4 is roughly millivolts, roughly. So here you can see offsets of 50 millivolts, less than 50 millivolts. This one's a bit more than 50 millivolts at the 0 point. But if I go ahead and I send 5 volts out, then this is the raw ADC value. Something else that's worth checking here is what the disting is actually outputting. So for that, I would take a multimeter and just quickly check it. So it says that it's currently outputting 5 volts. Just to be clear, you don't need a multimeter to do this calibration. This is giving me almost exactly 5 volts, right? So from this point onwards, I'm not going to use the multimeter except for maybe validation at the end. But just for sanity's sake, I want to check that the disting or the voltage source that I'm using is actually giving me what I want. So now I'm feeding in 5 volts. If I hold down P, it has captured the average value of the raw ADC samples on all of the inputs. Now I need to supply minus 5 volts. So I'm going to go ahead and do that. -5. And then I will hold N. There we go. So now you can see down the bottom here is using this input calibration that I just performed, what the calibrated voltage would be if the calibration was running with this calibration that we just generated. So now if I change, for example, to 0 volts on this thing, you can see down here, after the conversion, we're reading 4 millivolts or so on all of the channels. So this is much better than it was before, 50 to 100 millivolts. Now we're, for example, if I put 3 volts, they're all within like 1 millivolt, of that order. So I'm going to go back up to whatever. You can test the whole range. So now I can go down to, I don't know, here's -8 or +8. And this is the kind of tests that I do when I'm actually manufacturing these things, just to make sure that everything is correct. So now that we've done the input calibration, down the bottom here, you can see the generated calibration constants that are used by the calibrator module, and this is what you'll copy and paste into your own repository if you want to calibrate your own. The next point in here is it says I should press O to switch to output calibration. That's what I'm going to do now. I press O. And what it wants me to do is loop all of the outputs to the inputs. This is all in the instructions to be clear where I'm reading this from. It wants you to loop all of the outputs to the inputs. So I'm going to go ahead and do that. You have to be careful. You always want 1 to 1, 2 to 2, 3 to 3, and so on. What we're reading now is the raw ADC samples given to us by the outputs at this point in time. If we send, for example, +5 volts out, that's what we're currently doing. We're currently sending 5 volts out because we're not pressing this button on the FPGA. We're sending 5 volts out on all these 4 jacks. We get 5 volts on all of these jacks, but the 5 volt output is not calibrated yet. So what we read, for example, this 4.9, 4.89, 4.94, this is what we are sending because we just calibrated the inputs. So this we know is the true value of the outputs, and we need to calibrate this. So if I go ahead now and I press P, it will capture this. There we go. And now what I want to do is I want to press the button on the icebreaker. I'm going to press it. Now all of the outputs have gone negative. And now I will press N to capture that. There we go. And now in theory we've just created a calibration file. So I will take my shiny calibration here. I will put it somewhere. So here it is, right? So let's go gateware cal. Let's just change the default one. So default for revision 3.3 hardware is now this. You can see it's slightly different to the calibration that used to be in there. And so now, the next time we build an example, it will use our calibration that we just created. And so that is all of the steps in the calibration tool utility that we just followed. And what is important to note, I mentioned this before, if you check the output calibration with a multimeter, make sure you add a 100K load or calibrate with cal open load. So we calibrated with cal open load, so we don't need to add a load resistor to emulate us being connected to another module. So I'm going to press X here to exit the calibration tool. I'm going to go back and change the gateware so that we don't do this output calibration stuff anymore because we don't need to. And then I'm going to go ahead and build the mirror core again. So now I'm building the pass-through core, the same one that we started with, but this time we're using our custom calibration file. And I will disconnect all of the loopbacks here. Now if I go ahead and I connect the disting to one of the inputs, and currently, what am I doing? I'm inputting -5, so let's go 5. And then we want to check what it is outputting now. So before we were out by 50 to 100 millivolts depending on the channel, and now we are, this is a bit difficult because I'm kind of holding it with my finger, and my fingers have a non-trivial resistance, so they may actually change the results. I'm trying to hold it without it touching my finger, but here, so I have, just put this multimeter here, if you can even read it, there we go. And now I'm going to try and attach the probes. So we have almost exactly 5, that's like 2 millivolts or so away after calibration. And you can try it with some different values, so let's go, I don't know, like -8. -8. This here. And this is the error of the disting plus the error of what we just calibrated, so it's not going to be too crash hot depending on where we are. There we are, 20 millivolts out, so the closer to 0 you are, the better it will be, but it's definitely better than you will get out of the box, and it's also definitely good enough for playing with tuning oscillators and so on, at least in my experience, because there you're often operating between 0 to 5 volts usually if you're tuning things, but yeah, that's how the calibration process works. And that's about all I wanted to show today. If you are curious about some of the more advanced projects, as I mentioned before, you can go up to the organization and you'll find an example of running a soft core with some Rust firmware for DSP, using the PMOD as a USB sound card with the Luna USB framework in Python. You can even simulate your Verilog in a virtual Eurorack system. But as far as the basic repository goes, this is how it works. And if this is your niche, definitely have a play. You can either build this yourself, or I also ship these. So go to my website and you can buy one there. I hope this was useful to you. I have some other projects planned with this module, and thanks for thanks for watching this video, and I guess I'll see you next time.